Hello, Harsha. Am I audible to you?
Yes.
We'll wait for some more time. We'll start meeting shortly. We'll wait for a few minutes to join some more people, and then we'll start. All right, we'll start meeting. Welcome all of you. I am Vijay Rane. I'm a Prime Minister Research Fellow in IIT Delhi, and today we are here to discuss some problems based on the week 8 content, which is covered in the course essential of the oxidation reduction and carbon-carbon bond formation reactions and its application in the organic synthesis. So in this video, in this eighth week, professor has covered almost uh, many topics regarding the asymmetric oxidation, and particularly I'll show you here, particularly the Sharpless epoxidation to form the uh, epoxy alcohols. Further, also covered the Jacobson epoxidation, and also see the mechanism as well as the stereochemical aspects of the this reaction. Uh, and in the 38 video lectures, professor has covered regarding the Jacobson epoxidation as well as the introduction of the Sharpless asymmetric dihydroxylation, and further application of these Sharpless asymmetric dihydroxylation in the synthesis of some natural products. And in the end of this last week videos, professor has already started the asymmetric hydrogenation reaction and also the asymmetric reduction using the different metal-based catalyst. So before moving to some discuss the problem, if anyone have any doubt regarding the topic which is covered by the professor, so that we can discuss here. So before going to the next slides. Also, in meantime, if you have any doubt, please put that doubt in the chat box. So we'll discuss that one while discussing the some question that I have taken here for examples that we are going to solve. Let's start with the first Sharpless asymmetric dihydroxylation. Uh, I will not go in more detail because it's already covered by professor. So basically, in this asymmetric dihydroxylation reaction, enhances selective cis dihydroxylation of the olefins using osmium catalyst in presence of cinchona alkaloids based ligands. It's done, and it gives the, as discussed here, it gives cis dihydroxylation from the olefin. And what are the reagent here? It is used here is the K2CO3, which is the base to maintain the basic condition. Further, the K2OSO2, OH4, so which is the osmium based catalyst, and the ligand. So I have given the structure of this DHQ PHAL, that is the DHQ PAL, which is 1,4 bis 9 dihydroxy quinonine thalazine. This is the ligand which is drive the asymmetric dihydroxylation of the olefin. So we'll look for some examples of this asymmetric dihydroxylation, and we'll also see some its application in the synthesis of some alkaloids. So here, if you look at the mechanism of this dihydroxylation reactions, it proceeds through the 3 plus 2 cycloaddition reaction. So the osmium here, so the osmium tetroxide, which is the active ligand here, which is gives the 2,3 cycloaddition across the olefin. So as a result, so it gives the intermediate that I have shown here. So this intermediate one, in which the ligand drives the stereochemistry and the cis addition across the olefin. So these two hydroxy group shown, sorry, the oxygen atoms shown here, which is attached to the olefin in the same fashion, which comes from the osmium tetroxide, and further 2, 3 cycloaddition takes place across this osmium complex, and followed by the hydrolysis, which gives the cis 1,2 dihydroxy compound. So in this case, so the first thing that we need to discuss, keep in mind, is the addition takes place in the concerted fashion in the 2,3 sigma tropic kind of cycle addition. Further, the osmium tetroxide is the active ligand, active catalyst, which from which the oxygen atoms, which is the attached to the which comes in the product, that is the hydroxy uh, groups in the final product, and the ligand, which is that we have already seen, the DHQD PAL, DHQ2 PAL, which is the ligand is getting used for this Sharpless asymmetric dihydroxylation reaction. So if you look at the some examples of this dihydroxylation reaction, so this is the starting material that we have, and you can see here it has the epoxide as well as the hydroxyl group and the N3 as a one of the side group. So upon this performing this asymmetric dihydrogenation reaction. So the addition takes place in the syn fashion, and you can see the stereochemistry. Both the hydroxy group is directing the beta to the addition takes place in the syn fashion, and we get the product with the 90% diastereomeric excess. So we got about 90% diastereomeric excess. Why this is diastereomeric excess? Because already there are one, two, and three different chiral centers are already present in the molecule. So that's why it is here we have written the diastereomeric diastereomeric excess, that is represented in the shortcut like DE. So if there was no any kind of chiral center, only one chiral center, in that case we generally write the enantiomeric excess, that is the EE. But here there are already many chiral centers, so that's the reason the product form is the in the diastereomeric excess. Further, the second example here mentioned, so which is the alpha beta unsaturated ester, and it has the alpha beta unsaturated double bond, which is the olefin. So upon addition of the AD mix beta and the yummy SO2 NH2, that's the amine, that's the it maintain the basic condition. Further, in the reaction solvent like the butanol water in the 1:1 ratio, I mean, and at the room temperature in 12 hours, it gives the product. And the another one is the just the protection of the one of the hydroxyl group. So that's the another reaction. But upon these two steps, we get the 92% enantiomeric excess compound with the 92% enantiomeric excess. So this is the utility of this kind of Sharpless asymmetry epoxidation. So if you look at the third example here, so which is the simple olefin, and upon dihydrogenation with the osmium tetroxide based ligand and DHQD PHAl as a ligand, osmium tetroxide as a catalyst, and the DHQD PAL as a ligand, and NMO as a base. So, and the reaction performed in the acetone water solvent. It gives the 90% yield of the dihydroxyl product, and with the enantiomeric excess about 70%. So why in this case the enantiomeric excess is low? This is because this molecule is the not that much bulky. So everything happen in the asymmetric fashion. The driving force is the steric repulsion between the bulkier group. So in this case, there are not such bulky group. If you look at the previous cases, previous examples, there are some bulkier groups. But in the simple this case, there was not much bulkier group. That might be the reason. The enantiomeric excess is slightly less compared to the previous examples. Although the reaction works goes in the asymmetric fashion, because the enantiomeric excess is the 70%, so it implies about 70 plus like 50, so it's like 85% of the product is getting formed in the one enantiomer only getting formed, and the another 15% the other enantiomer. So these are some examples of the dihydrogenation, and you can remember these examples, how the dihydrogenation occurs in this in this type of starting materials. So again, the in the similar fashion, this uh, as seen dihydrogenation, there is the same Sharpless asymmetric amino hydroxylation reaction, which is although not covered by professor, but it is one of the important reaction, and it gives different kind of the structurally important product, final product, and which has good application in the different synthesizing different medicinal active compound and other active pharmaceutical some ingredients. So that's why we'll also look for the this reaction as well. So which is asymmetric amino hydroxylation. So in previous case we see we get the syn dihydroxyl compounds, but in this case what happens? So the osmium mediated cis addition of the nitrogen and the oxygen to the olefin takes place in the Sharpless asymmetric amino hydroxylation. This is the first point. The second one is the reduced selectivity may be controlled by the ligand. So in this case, in previous case, both at the both positions. So let's say this is the R1 and this is the R2. And if you look at this is the first carbon and this is second carbon. At the both one and two position, the two hydroxyl groups is attached. But in this case, there are two different groups. So one is the amino and one is the hydroxyl. So in this case, the residual selectivity is the issue. But if you look at the different ligand, there are in some examples we get quite good residual selectivity, and this residual selectivity is generally controlled by the ligands, which is and further the nitrogen source are the X stands for here. There are many groups I have given. So X, N, Cl, Na. So that's like a kind of salt. So this is the one of the salt that I have here given mentioned. One, two, three, and so these are the some different kind of the nitrogen sources are given. So one is from the sulfonate. This is the sulfonate salt, right? So it paratoluene sulfonic acid that we already know, right? So it comes from the such sulfonate salt. Further, it is like amide, and which is the salt of the this group is the amide, right? And from using such reagent, we can this is the which serves as the source of nitrogen. Further, again, there is another nitrogen source that I have enlisted here. So you can go for you can have a look regarding these nitrogen sources. So in this case, so the chiral ligand, it might be the DHQ-DPAL or DHQ-PAL, depends on in many cases there are multiple examples, multiple ligands are available. So yes. So for as of now, in this example, you can consider this as a ligand. So you have the trans olefin here, and you added the ligand, further the osmium catalyst, and the nitrogen source. In this case, is the you can take any of the nitrogen source. It gives the hydroxy and the NHX. That X stands for this entire other group. So in this case, let's say this is the entire X, the group which are written here. So these are the X equals to, these are the all the groups. So in one place it is a hydroxy group is attached, in another amino group is getting attached. So that's the reason it called as a as amino hydroxylation. So if you look at the catalytic cycle of this reaction, so in which this osmium tetroxide and the nitrogen source it forms a intermediate one which on the further reaction with the ligand, it gives the intermediate 2, which has this NX as well as the ligand attached. So in this case, there was only the NX attached. The nitrogen bond to the osmium with the double bond. Further, the intermediate 2 react with the olefin. So after reaction with the olefin, it forms the intermediate 3. So this intermediate 3 has and the direction by which the intermediate attached. So in this case, R1 and R2, you can see here the R1 and R2 attached in this fashion, which is driven by this ligand. So depends on the which ligand we are using. So this drive the formation of this intermediate step 3. So further, this intermediate step intermediate 3 convert into the intermediate 4 upon elimination of the another equivalent of the this nitrogen source. It gives the intermediate 5, and upon hydrolysis, it gives the amino hydroxylated product, right? And again, the cycle goes on. So in this manner, so the first ligand addition followed by the addition of the olefin, and then the internal, you can see here. So it is a internal rearrangement. So this bond gets shifts to from the osmium to the oxygen. It forms the intermediate bond, and upon the addition of the another equivalent of the nitrogen source. So this is the second equivalent of the nitrogen source is getting attached, and upon addition, it gives the intermediate 5. So this intermediate 5 upon hydrolysis. gives the or dihydrox sorry hydroxyl amino product, and this osmium complex is go in the again the second cycle. So in this manner we get from the normal olefin. So from the olefin we get the amino hydroxyl product. So let's say here there's R1, R2, and this is the hydroxy group, and this is the amino group, NH. Let's say X. This X depends on the which nitrogen source that we are using for the reaction. So this is the same type of reaction as earlier seen as like asymmetric Sharpless dihydroxylation. This is the only difference is the instead of dihydroxylation. So as we have seen here earlier, this asymmetric dihydroxylation we get from the olefin, we get the 1,2-dihydroxy compound. But by using this asymmetric amino hydroxylation from the starting olefin, we get the amino hydroxyl compound. So there are different nitrogen sources, and depending upon the what kind of product we want, we can select the nitrogen source from here. So further, this was the second reaction. First is the dihydroxylation, and so this is the amino hydroxylation. We can see some examples. Let's take the simple examples. We have the nitrogen source here, so which is the simple simple carbamate type of structure, and it react with the olefin. In the with the ligand in this case, which is used is the DHQD twice PAL. So using this is as a ligand. Further, this osmium as a this osmium catalyst, and the reaction solvent is the isopropanol water in 1:1 ratio. It gives the cis hydroxylamine. You can see the stereochemistry of this bond. So it gives the syn stereochemistry, and so in this case we got the product. It gives the yield 63% enantiomeric excess, and the reaction goes in the 51% yield. So the 63% enantiomeric excess, it also it indicate the asymmetric amino hydroxylation of this starting material is getting occur. So if you look at the another example here, so another example, this is the example in which the reduced selectivity is also matters. The because in the previous example, the starting material which has the, you can see here it has the plane of symmetry or the symmetric molecule, and it doesn't matter at which position the amine group is attached and at which position the hydroxyl group is attached. But if you look at the ester, this compound, so in which the the stereochemistry you can see here. So the hydroxyl group attached to the near to the phenyl, and the nitrogen containing the amino which attached to the NHCBZ attached to the addition to the ester group, right? So this is because of the selectivity due to the DHQD twice AQN as a ligand. This ligand drives this radioselectivity in this case. So this is the example in which the radioselectivity also the one of the uh, point that you can see. So this is also radioselective. So this is radioselective, also the stereoselective, right? So you can see with this example, radioselective addition takes place across the double bond. Also the stereoselective addition of the hydroxyl as well as amino group takes place around the double bond. Further examples you can see here. So this is the simple starting given, and which is again created with the NaOH and urethane in the osmium catalyst, osmium based catalyst. So further, the ligand used in this case is the DHQ2 PAL, and it gives the mixture of the product. So this is not a radioselective, right? This is not radioselective, but although this is not radioselective, no, not. not radioselective, although it is not radioselective, but upon uh, treatment performing this reaction with the base in the alcohol solvent and followed by the acid treatment, it gives the same product. So both these gives the same product, because what happens upon addition of the base, what it abstracts the proton, it gives the addition across the cyclization takes place. So the in the both way, if the cyclization takes place, it gives the same product, and that's the reason. So upon addition of the base followed by the acid, it gives the same product in both the cases. So this is the one of the interesting example. Further, as of now, we have seen asymmetric dihydrogylation, again the asymmetric amino hydroxylation, and this is the asymmetric epoxidation reaction. So this is also Sharpless asymmetric epoxidation. So in which the enhanced selective epoxidation of the allylic alcohols using third butyl peroxide and titanium tetraisopropoxide and optically pure diethyl tartrate as a reagents. It gives the stereoselective epoxidation of the allylic alcohols. Allylic alcohols means the alcohol which has the adjacent double bond, right? So the carbon atom to which the hydroxy group is attached, that carbon atom should be attached to the double bond, that is the olefin. In that case, it gives the asymmetric olefination, because this hydroxy group has the a role in the formation of the intermediate state. So you can see here. So this is the active catalyst and the transition state. So this titanium isopropoxide, this is the titanium and isopropoxide you can see here, which create which upon reaction with the diethyl tartrate. So this is the part of the diethyl tartrate, and so upon this reaction, sorry, it forms the active catalyst like titanium isopropoxide and the diethyl tartrate. It forms this active catalyst, and which drives the stereoselective or the inertial selective oxidation of these allylic alcohols. So the catalytic cycle already covered by the professor, right? So I will not go into more detail, but you can see here. So this the peroxide and the allyl alcohol, it forms a intermediate one around the titanium. Further, this intermediate uh, get converted into the intermediate 2, and then followed by the intermediate 3, the intermediate 4, and at then it forms the intermediate 5, and then the hydrolysis gives the epoxide with the enhanced selective in the nature. So that's the catalytic cycle and the reaction mechanism of this asymmetric epoxidation reaction. And if you look at some examples of this asymmetric epoxidation, so let's take the first example in which you can see the L diethyl DIPT and titanium isopropoxide with the TBHP, that is the tert-butyl hydrogen peroxide. The it gives the 89% yield with the 98% in enantiomeric excess. So this is the one of the intermediate, and this is further converted into the this is the active starting material for the formation of the SS reboxetine. So which is the this reboxetine is one of the active medicine, and so the starting required for this reboxetine is getting synthesized by using such Sharpless asymmetric epoxidation reaction. So you can see there some synthetic utility of this one. So there are many steps in between involved to convert the starting to the reboxetine, but the starting required is the this RR epoxide, so which is getting prepared by using this Sharpless epoxidation reaction. Further, another example here, which has the sugar. side group, and with the di minus DIPT, the titanium isopropoxide, and the TBSP. So it gives the epoxide. You can see here in this fashion. So this is how the stereochemical asymmetric epoxidation useful for the formation of the product. You can see which has synthetic utility, and with the example of this riboxetine, you can see this intermediate you can convert into the useful final product. So if you look at if I just summarize this, how this uh, DT works. So if you just write the structure of the year starting in this fashion, in which the hydroxy group is located in this manner and R1, R2, R3 in this way. So the attack takes place from the rephase. Then we get this attack takes place with the RR diethyl lateral, that is the plus DET. So that gives the alpha directing epoxide. And in this case, when the psi phase attack takes place on the psi phase, which is by the minus diethyl tartrate, and the beta epoxide getting formed upon the reaction. So, so this is how the epoxides are formed using the allyl alcohol. So you can see here, this again, I have written, just summarize this, all the, how the surplus epoxidation of the allyl works and how the catalytic cycle works. So you can see here, you can take some lead here. In the first step, it occurs like both the peroxide and the alcohol forms an intermediate, and the substrate and oxidant replace two OIPR ligands, that's isopropoxide ligands. Further the oxygen atom is direct the alkene. The alkene is above the peroxide, so oxygen atom direct because of this hydroxy group. The alkene is getting directed and towards the peroxide. Further, the two equivalent of peroxide ligand replace the departing product. Hence, the catalytic is regenerated. As the catalyst, you can see regenerated, and the product we are getting is the alcohol, which is from the peroxide, right? And the alcohol epoxide product. So, how to keep this in the easy way? So many time, let's take the example theoretically. If someone want to give the answer just by looking at the structure. So by considering this entire this intermediate step and this kind of active catalyst and this entire transition state, it is difficult to give the product. But if you look at the in the easy way, so just draw the structure in this manner with the minus diethyl tartrate attached from the this psi phase and plus diethyl tartrate attacks on the this three phase. So in which you need to align the hydroxy, the Z group, and the E group in this manner. So in the above, alcohol in the top left. So alcohol you need to get in the top left delivers from the so plus diethyl tartrate deliver epoxide from the downside, and minus diethyl tartrate delivers the from the top side. So that's you need to just consider. So make sure you write the alcohols on the top left. So this you have to write this alcohol on the top left, and let's take, so this is the double one, right? So this is Z side, that is on the syn side of this alcohol, right? So here also you have to write the alcohol and this group on the syn side, and this is the on the trans side that we need to as draw as it is, and then you can do the simple, just remember this minus dt attacks on the top side plus dt attacks from the bottom side. So that's the simple trick here that you can remember. So but only thing, you need to write the alcohol on the top left of the, this is the important top left. So you have to write this in the top left. That's the compulsion in this case. If you write on the opposite side, then you will get the opposite product. So you have to remember here something. So that's the write the alcohol on the top left. followed by the write the corresponding E and Z group. Then you will get the correct answer. So further, using this DT diethyl epoxidation, sorry, the surface asymmetry epoxidation. So we'll see some of the that's the gypsy moth pheromone. So this is the gypsy moth pheromone. So it is the enantiomer pure plus dis dispar disperlure attacks. So that's the you can see the name here. So this is the chemical which will be the enantiomer and it attract the female mate, not the and the racemic. If it has either in the racemic form, it inhibits the attraction. So you can see the exactly opposite effect. So that's the reason you can see the why the enantiomer selective uh, the enantiomer pure compound is required. So in this case, you can see here. So this is the starting material. We treated with the we converted to the epoxide. This is the in the 80% inospheric excess. Further oxidation with the PDC. So the PDC this makes the PCC or PDC. It makes the aldehyde, and further this aldehyde treated with the Wittig salt. It gives the this entire structure. So addition takes place across the aldehyde, and upon reduction of this double bond, so this double bond get reduced. It gives the enantiomer plus disparlor as a that's the pheromone that getting synthesized. So in this manner, you can do the synthesis of this uh, enantioselective alkaloid, right? Another you can see. So see, with this epoxide, I will show the product which are the intermediate for the different synthesis of different kind of alkaloids. You can see here are the different kind of medicinal active compounds or the natural products. So this is the starting, the first one. So upon epoxidation, it gives the initial select 45% yield in the enantiomeric excess about 95%, and which is the intermediate for the methimycin natural product. So for the methomycin, you need to have this enantio pure the epoxide. Further, you can see the another example upon which is again the starting material for the erythromycin. And another example is the you can see here. So which is the licotrine as a product. So this epoxide is used for the this epoxide is intermediate for the synthesis of licotrine, and that this the already we have seen already for the pheromone, right? So these are the some intermediate epoxides which are the intermediate for the synthesis of different kind of natural products. Further, if you go toward the asymmetric epoxidation of the alkene using the this is the another fourth type of reaction. So epoxidation of the alkene using the amine selen complex. This is called as a Jacobson epoxidation, and you can see the manganese based ligand here, and further hypervalent iodine as a source of oxygen, and it does the enantioselective selective epoxidation. And you can see there are multiple examples here that I have noted here. So this is the first example. So you can see this the using this manganese based ligand and the hypervalent iodine reagent. So it gives the initial selective product formation, and you can see different kind of epoxides which gives the different type of olefin which leads to the formation of the product in the initial selective fashion. So about you can see 98% numeric excess, about 94% excess in the many examples. So This was the some epoxidations or the oxidation reaction. The first one we have seen the Sharpless dihydroxylation. The second we have seen the Sharpless amino hydroxylation. The third we have seen is the Sharpless asymmetric epoxidation. And fourth we have seen is the Jacobson manganese based epoxidation. So as of now, we have seen these four type of oxidations on of the olefin, which is the Sharpless asymmetric dihydrogenation. Another is the Sharpless asymmetric amino hydroxylation. The third reaction we have seen the Sharpless asymmetric of epoxidation, and the fourth is the Jacobson manganese silane epoxidation. So this was the some of the epoxidation, so the oxidation around the olefin. So if you anyone have any doubt, then we will discuss that one. So before moving to the next topic is the asymmetric reductions. So before moving to the asymmetric reduction, so anyone have any doubt? All right. So we have already seen these four type of reaction. So all these four type of reaction is like on the olefin, right? So now we'll move towards the some asymmetric reduction reaction. The previously four reaction, these are all the oxidation reaction. But now we'll see some sort of reduction reaction, and we'll start with the some catalytic asymmetric reduction of on the carbonyl. And before going to start directly, so we'll see some the uh, asymmetric catalyst that drives the asymmetric. reduction of this carbonyl. So this is the first catalyst which is developed by the uh, Noyoru one. So only for the directed reactions and with the H2. So H2 gas that we need to use for the reduction. So this is the ruthenium based catalyst, ruthenium binaphthyl catalyst, and this is used for the reduction of the ketone in asymmetric fashion. Further, the Noyoru second generation catalyst, which is the more general catalyst, and which is in which the again the ruthenium with the ferrocene, not the ferrocene with the uh, ruthenium catalyst with the can see here, which is the amino and the this entire kind of asymmetric catalytic core is getting used for the reduction, and the another one is the based on the binap again with the ruthenium and the diamino side group. So this is the Noru second generation catalyst, and these are the chiral amino acids they are getting used. And in this you can see with the hydrogen that we need to use, and with this isopropyl alcohol that we can use for the reduction as a reducing agent. So with the isopropyl alcohol and the hydrogen. Further, another catalyst is for the reduction is the CBS based reduction. So which is like Kore, Bakshi, and Shibata catalyst. So the CBS catalyst is like the BS is the complex. You can see here. So this is the complex, and this is also the do the job in the similar fashion. So let's say we have some ketone with the R group, two R groups. So obviously one is the larger and one is the smaller. And in this case, the hydroxylation, so the reduction takes place. So the attacks of the hydrogen takes place on the beta fashion. So the hydroxyl group you can see here is directing alpha. So definitely the hydrogen which is attached, which is the directing beta. So in this is the CBS based reduction. So you can see the active catalyst used for this reduction reaction is the this kind of the proline based ligand with the boron as a boron in between the nitrogen and oxygen. So these are the some catalyst that getting used for the reduction of the carbonyl compound. So if you look at the in the more detail of this CBS reagent and some how the reduction occurs. So here are the some steps involved. So this is the L-prolyl. It is the synthesis of the CBS reagent starting with the L-prolyl. This L-prolyl upon after few steps it can get converted into the this boron intermediate. So the starting is the L-proline obviously. So this is the starting material, and upon reaction after few steps we get this the CBS reagent. So this CBS reagent when to react with the BH3 it forms the boron adduct, and this boron adduct is responsible for the asymmetric reduction of the carbonyl compounds. So the E.J. Corey, the Nobel Prize in 1990 for retrosynthesis synthetic analysis of this boron, and uh, for the retrosynthetic analysis, E.J. Corey got the Nobel Prize in 1990, and they have used for the CBS based reagent for synthesis of some natural products and all. So you can see the side view of this boron adduct. So this is the boron adduct which is the responsible for the reduction of the hydride transfer across the carbonyl compound. You can see one of example here that I have mentioned. So this is the first example in which you can see there is a carbonyl group, and you added the CBS catalyst about 10 mole percent with the BH3THF as a reducing agent, and you can see the addition takes place of the hydroid on the beta fashion, and with the enantiomeric the product got with the enantiomeric excess which is 93%. So it is definitely a quite good enantiomeric excess. So an efficient catalyst for the reduction of the ketones is the Kore, Bakshi and Shibata catalyst. So further, this catalyst bring the ketone and the boron together in a chiral environment. So you can see the intermediate and the intermediate active catalyst form. And when it react with the ketone, it gives the uh, enantioselective selective reduction. Further, this reagent, as earlier discussed, which is prepared from the proline derivative, which is a very commercially available starting material. Uh, and the reaction utilized nearly 10% of the heterocycle of the utilizes nearly 10% heterocycle and the stoichiometric amount of the boron and works most effectively if there is a big difference between the each substituent on the ketone. So definitely on the ketone there will be only the two different types side groups. So let's say R1 and R2. If there is different in the sizes of these two R1 and R2, then the enantiomeric excess is definitely going to increase in the product. And the mechanism is also quite elegant. That is a quite very simple reaction mechanism. You can already have seen here. So this is the boron adduct, and you can see the mechanism that I will show here. So let's say we have the this catalyst and react with the BS3 in the THF, right? It forms this boron adduct, and you can see here BS3 attacks on the nitrogen of this proline. So upon reaction with the ketone, so ketone definitely have two R groups. R might be aryl or alkyl. So in which one is the slightly long, large, and one more might be smaller. So if it is non-equivalent R groups, then one definitely have the size difference. Both group may have the size difference, and as a result, it drives the formation of the transition state in which the selective transition state in which the larger group directing away from the in the center catalyst, and this the R's that is smaller group which is the will be close towards the this catalyst. So the coordination of the aldehyde activates the phases, places it closest to the boron, and this chair-like transition uh, state in which the large substituent is the pseudo equatorial position. So that's the key driving force here. So the large group goes to the pseudo equatorial position. So that's why the steric crowding is less in this type of transition state. And further, hydride transfer takes place from the boron to the carbonyl carbon, and as a result, and further, it gives the elimination of this hydroxy product, which is the reduction product of this ketone, right? So upon reduction, this hydroxy compound we got, and in which you can see here the hydride is the directing beta and the hydroxy group directing the alpha oriented in this case, right? So that's the product, which is and in which you can see the enantioselective selective, this transition state forms, which gives the enantioselective selective hydride transfer across the carbonyl compound. So that's the simple ligand reaction mechanism as earlier discussed with this CBS based catalyst. CBS based catalyst. So in the if you want to directly give the product by just seeing the reaction, sorry, by just seeing the starting, and you just want to directly assign the product. So it is very difficult to go step by step by making the transition state and all. But in the easy way, you can do that. You do in this fashion, like write the large group on the right hand side, and they write the ketone with the larger group on left hand side with the smaller group on the right hand side, and just add let's say we have the minus CBS, then you can directly mention hydride will be on the beta and the hydroxy on the alpha in the product. And if you use the plus CBS, in that case, you can directly you can write the product with the hydroxy group, which is directing beta. So make sure you write the larger group on the left side and the smaller group on the right side. And the minus CBS based catalyst gives the alpha directing alcohol, and plus CBS based catalyst give the beta directing alcohol. So you can keep this noted. So this is a kind of shortcut to remember the just by seeing the structure of the starting, you can directly assign the product. So if you look at the some of the examples, so let's have the this is the one of the ketone, and let's say this is alpha unsaturated ketone, and this upon reaction with the CBS catalyst and BH3. That the in this case they have not used the BH3, they have used this borane. So the hydrate transfer of this BH, that's the hydrate source, and in the toluene at minus 17 degrees Celsius, it is the 96% enantiomeric excess. So you can see here, so about 96% enantiomeric excess, which is like it gives selectively 98% of one enantiomer, right? So you can see how this reaction is very effectively gives the reduction, right? And upon so this is the this product that the product, so which is the active starting material for the synthesis of the prostaglandin E. So you can see this is how the starting materials is getting prepared from the this commercially available ketone, alpha saturated ketone, and which on the stereoselective reduction gives the hydroxide, and which is the starting material for the synthesis of this prostaglandin. So further another structure you can see here. So this is the starting into which this ketone. So this is the you can see there is quite bulky one R group, and one is the R group is the smaller R group, and you can directly by using this you can directly assign the product. So this is the you can see the product getting formed, and this product is the intermediate sorry, the starting material for the synthesis of the disinodol dicy diacyldiolide product. So this is the starting material for the diacyldiol, right? So and this is how the upon the asymmetric reduction with the CBS based catalyst, the starting alcohols with getting prepared. So this last step is the just reaction with the oxygen and the light, that the H nu, and using the rose bengal as a photocatalyst, you can see. So this reaction gives the 98% of this diacyldiol product. So this is a very simple reaction. You can use the CBS catalyst and the BH3 DMS as a producing hydride source in the toluene solvent at minus 70 degrees Celsius, right? So these are the some sensitivity of these CBS based reduction reactions. So does anyone have doubt in this kind of CBS based reduction? So you just keep in mind. So write R group in the right hand side. So this is the let's say the ketone, and in which the larger group on the left hand side and smaller group on the right hand side. So when you add the minus CBS, then the hydroxy group is on the beta, sorry, the alpha, right? Right. The hydroxy group is on the alpha, and when we add the plus CBS, then the hydroxy group is on the beta. So that's the simple you can just remember. Simple thing that you can remember just by using the this kind of uh, shortcut. You can have the you don't really require to draw entire all the transition state, but for concept purpose you can remember always the this transition state. You can see how this six member transition getting formed, and the larger group which is in this chair like transition state, how this larger group is directing toward the pseudo equatorial, which drives the stereosymmetric, sorry, inertia selective hydride transfer across the carbonyl compound. All right. So if anyone have a doubt, please let me know. All right. I will take some more examples here. And in meantime, if anyone have any doubt, then you can ask I will see the chat box if there is there any doubt here.